So, hello everyone. Welcome to the NPTEL course of Foundations of Cryptography. This is going to be your week 3 tutorial session because due to some unavoidable circumstances, I could not take the class on scheduled date, that was last Saturday. So today is going to be the live session for week 3, and tomorrow again at the regular time from 6 p.m. to 8 p.m. there will be the live session for week 4. Okay. So let me share my screen and I will start discussing the questions. Also, because I saw that your assignment submission deadline for the first 3 weeks have been over. So today I will discuss just all the assignment questions for the first 3 weeks that were posted on NPTEL website. And tomorrow again we will discuss the topics, questions from the topics that are given in week 4 lectures. Okay. So today is going to be the broad range of starting from week 1 to week 3. Okay. So let me share my screen. Is my screen visible? Hello. Okay. Thank you. So first we will discuss the assignments from week 1. Okay. So this was the first question. Which of the following is or are not perfectly secure encryption schemes? Okay. So I think answers are already posted, but we will I will discuss this question so that if there is some doubt or something, you can clarify again. Okay. So starting with this question, so maybe I don't know, like affine cipher. So I will just discuss briefly how all these 4 ciphers works, and then how many among them are perfectly secure or not. Okay. So starting with the Playfair cipher. Yes, hello. Anyone is saying something? Okay, I guess that's nice. So for Playfair cipher, so this is a kind of cipher where your key is of some 5x5 table form. Okay. I will not go into the details of this cipher because you can anywhere just search, you will get them in the book, or simply search in Google and you will get detailed document on how they work. Okay. So for Playfair cipher, the key is of this form where each of the box contains unique English alphabet. So we have 26 alphabet, right? So usually out of 26, distinct 25 alphabets are filled up here in some particular method. So let's say you first choose a keyword, right? The way key generation works here, you choose some keyword. Let's say your keyword is keyword itself, okay? keyword. Now, here it happens that none of these 7 letters present in this key are repeated, okay? If there would have been a repetition, so for this, how the key is work, so here you will fill up this 5x5 box in this manner. So you will start filling up like this. So keyword, nothing is repeated. And then how many are left to be filled up? So 7s are filled up, and another 18 boxes are there to be filled up. So you will just fill them up sequentially starting from A to Z, except the letters that has already occurred. Okay. So let's say A has not been occurred. So you will keep A, then B, then C. D has already been occurred. So E has also been occurred. F is not there. G is not there. H is not there. I is not there. And also notice another thing, because there are 26 alphabets and we have the places for only 25 letters here. So usually J is omitted. That is just a standard convention, nothing else. So J is omitted. So except J, all the rest 25 letters of English alphabet are filled up in this box. So the way we are continuing, first you fill up the keyword itself horizontally till whichever point it reaches, avoiding any double occurrence. And then you fill up rest of the alphabet sequentially. So A, B, C, D already occurred, E already occurred, F is not there, G is not there, H is not there, I is not there, J you omit, and K has already occurred. So like this, L, M, N, O is there, P, Q, R is there, S, T, U, V, W is there, X, Y is there, Z. So that is how you form a 5x5 table here. And then this Playfair cipher is a diagram substitution cipher. Okay. So what is diagram? Now, diagram is any two size group of two letters, right? So let's say AB is a diagram, BC is a diagram, BD is a diagram, like that. So any couple of two letters, okay? Now you substitute them with some other pair of letters. How this substitution occur? There is defined encryption rule for this. Like if the two plain text, so you have some text to encrypt, right? Let's say I am going. Ignore the spaces for now. So let's consider some word. Let's say okay, king. Okay. Now there are two diagram here. First is ki and then ng. Okay. So how do you encrypt these two? Ki will be mapped to, let's say, where k is here in this box, k is here, and I is here. So the rule is, if k and I does not occur either in same row or in same column. So neither is the case here, right? K and I are not in same column, also are not in same row. So you will consider this rectangle, okay, covering K and I at two of diagonally opposite points. Now horizontally, K has W at one corner, so K will be mapped to W, and I is horizontally aligned with F here. So I will be mapped to F like this. And for NG here, N and G are here column wise in the same column. So the rule is, you will take the element below that box. So N will be mapped to U, which is just below the box of N, and G will map to be N. So like this it occurs. Also the rule is for like if there would be a plain text of this form, A and C, and here you see that A and C are in the same row, so A will be mapped to its right element, so A will be mapped to B, and C will be its right element, which is R. So like this encryption is defined. So you can find these details anywhere, but the point here is whether it is perfectly secure or not. Now, as you can see, there is this is some kind of substitutions, right? So using some analysis statistically, you can always find some way to find the backward direction how the ciphertext will map to the plain text, right? So this will not be perfectly secure. So several possible attacks on this Playfair cipher you can find. Now coming to Varnum cipher. So how does Varnum cipher works? So here basically uh, you have, let's say, some message. Okay, again we are talking about English alphabet. So again, let's say message is king only. Now you always choose a key. Also, you map the English alphabet to its corresponding position value. So let's say A to Z, all these alphabets have some corresponding numeric value. So A mapping to 0, B mapping to 1, so on till Z mapping to 25. So you map K accordingly to the numeric value representing its position in the English alphabet. Same goes for I, same goes for N, and for G. Now you get some numeric value here, right? For example, for G, the value is 7. So you take the binary representation of that value. Okay, like 7 is mapped to 111 like this. And also there you select some key K, which is again uh, 4 letters from English alphabet. Why 4? Because the key has to have the same length as of the plaintext M. So you choose some key. Let's say kite is the key. Okay. So again, the key also, each letter occurring in the key also has some numeric value in the English alphabet. Again, the value, positional value for K, I, T, and E are taken, and each of them are converted to its corresponding binary values. So all the 4 letters have its binary representation of its positional value here. And for key also, you get its binary value for the corresponding positional value, and then you XOR them. So you XOR them and get some string, and then you map them back to corresponding English alphabet. If uh, you find the value after XORing to be greater than 26, you just subtract 26 from that once, and you get a value which can be easily mapped to some English alphabet, right? Now, the main point here is that how do you feel whether it is a perfectly secure encryption or not? So maybe I can discuss that the known perfectly secure encryption scheme that we have seen in the very beginning is the OTP scheme. Why OTP is perfectly secure? Because key is one time, right? So the key K is never used twice. It is always like for every message M, you generate the key K independently of key for another message. So each time K is generated independently and uniformly randomly over the key space, such that key space has the same space as of the M. So if M has length L bits, your key will be chosen from this space, right? L bit binary string. So the key K has always the same length as the plain text, and key is never repeated. So that's the reason that you can, even after seeing the ciphertext, you can't guess anything about the underlying key. Because even if you see some other ciphertext or some other plain text, each time the key K is changed, so you have no information about the key K, and hence you can't know any extra information about the distribution of the plain text, possible plain text underlying that ciphertext. So that is the policy of perfect secrecy, right? The condition of perfect secrecy was that probability of M being M, the message being a particular message M, when you see a ciphertext C, is exactly equal to the prior information that you have about the distribution of message space, right? So this is the condition for perfect secrecy, which is satisfied in case of OTP scheme. And here also in the random cipher, if you look at this closely, so here also your key is chosen of the same length as of the plain text. So Also, the key is freshly chosen every time. You see the message, you find the same length key, which is in the form of some English letters. So, and then you sort them and do some particular operations. So this has the exact same flavor as of OTP, and you can just mathematically see on your own that this satisfies this condition of perfect secrecy, because every time you see some ciphertext C, there is always a chance of finding some corresponding key such that any message M from the English, any message A to Z from the English alphabet can be mapped to that particular ciphertext C with help of some possible key. So you cannot guess the exact message underlying that ciphertext. So that's how Varnam cipher actually satisfies the property of perfect secrecy. Coming to affine cipher and engineer cipher, so probably you already know about these two ciphers. So for briefly saying, affine cipher is nothing but like substitution cipher. So for all your English letters A to Z, they will be permuted to some other value. Some random permutation will be there, or A will be substituted by some other English alphabet, B will be substituted with something, and in this mapping, so each of the letters A to Z will occur exactly once, such that this is a permutation, right? So now, according to the like analyzing the frequency of English text and the property that let's say the letter E occurs most frequently in a standard English text. Now, whatever E is substituted with in this particular permutation, that particular letter will be occurring most frequently given some large ciphertext corresponding to some large English plain text, right? So, doing frequency analysis on that can simply give you back a very good idea about what is the actual permutation used. Okay, so you can actually attack this cipher quite efficiently. And then coming to engineer cipher here, so affine cipher is clearly does not satisfy the property of perfect secrecy. Okay, and engineer cipher here also uh, you have a fixed key length. Okay, the key is again some English alphabet. Some key will be there. Let's say flag is the key. So this has length 4. We call this the period. And you have some long plain text. Okay. Uh, so you have some long English plain text, and let's say I am going kind of this. So each letter in this plain text will be associated with the corresponding key bit, and then again like this it will go on. So uh, positional value of I will be XORed with positional value of F, or so it will be added actually. Positional value of I will be added with positional value of F, and we take the modulo of them, so we get some another English alphabet correspondingly. Positional value of A, which is 0, will be added to positional value of L in the English alphabet, and mod 26 will be taken. So some English alphabet will be mapped here. So like this, it goes on. Once this period of key is finished for one time, then again we use the same key for encrypting the corresponding subsequent plain text. So O will be positional value of O will be again XORed with positional value of F, and we get some other English letter as the ciphertext. Like this, it goes on. Okay. So note that here key length is actually not same as the message length. You repeat the same key uh, while encrypting a large English plain text. So this does not satisfy the condition of perfect secrecy, which says that your key space uh, cannot be lesser than message space to achieve perfect secrecy. Okay. Rather, in the Shannon theorem, you get that all the message key and ciphertext space are same, right? That is a necessary condition for achieving perfect secrecy, which is clearly not satisfied here. Now, so basically, among all these four options, this is the only perfectly secure cipher. Okay. So, uh, let me now proceed to the next question. So, I think this answer is already known to everyone. If any one of you want to unmute yourself and tell the answer, also explain them, I would appreciate. So, I will wait for just 1 minute, because this is the very basic principle of perfect secrecy, already have been discussed in last live sessions also. So any one of you can tell me which are the answers and why those are true. Anyone among the participants? Okay. So basically, this is the very basic condition for perfect secrecy, as I already just discussed in the previous questions also, that uh, the fundamental thing of perfect secrecy says that whenever an adversary sees the ciphertext corresponding to some message M, it sees the ciphertext. Of course, it belongs to the ciphertext space, right? And this capital C is a random variable which can take any value from this ciphertext space. Now, if it happens that the ciphertext takes this particular value, small c, from the ciphertext space that adversary can see, after seeing that, what information it can infer about the underlying plaintext message. So, the probability that the message underlying this ciphertext small c is small m, which is some particular message from the message space, this probability should be exactly equal to the probability that this message is small m when you have not seen the ciphertext. So what it practically implies is that uh, viewing the ciphertext does not really help you getting some extra information about the distribution of message space. So this is a very basic condition for perfect secrecy. And apart from this, if you closely observe, this also is another valid option for perfect secrecy. Why is that? If you remember that the perfect indistinguishability, what it says is that uh, probability that encryption of some key from the key space for some message M0 is mapping to a particular ciphertext C should be exactly equal to the fact that some another message M1 maps to the same ciphertext C using some key from the key space. So this is capital K, not some particular value of small key k. It can be any key from the possible values of key. So, but this probability that the ciphertext is C when the underlying plaintext is M0 and the ciphertext is C when the underlying plaintext is M1 should be exactly same. That is what this second condition says. So basically, here second and third options are the correct ones. Okay. Okay. So here is another application type questions. It says, assume you are given a 500 character encrypted message encrypted in Virginia crypto system in which you know the plaintext word cryptography occurs exactly 2 times. And we know that the ciphertext sequence, this, right? So note that it has the exact same length as of cryptography, right? So there are 12 letters in it. So the same sequence is repeated twice, and we know that this ciphertext sequence is the encryption of cryptography. Okay, now the first occurrence starts at character position 24. So this string first occurs starting from position 24, and the second occurrence starts at character position 198 among the 500 characters. Okay. So what is the length of the key used for encryption? So as I just discussed in question 1, what is Vigenère cipher? So you have a English alphabet, a English text, and you have some fixed length key, right? And so you repeat the key values, right? So here your key ends, and then again for the next particular value, you start using the same key, right? So let's say the key is empty. Okay, so again, you use the same key value. Like this, it goes on. Now, if you just observe that the same string occurs in the ciphertext, first occurrence. So I will just demonstrate how the situation is here. So first at position 24, you observe that this string starts occurring, and then 198 position also this starts. Okay. So let's say, like, if it would have been the case that the key size is 4, right? So in the last slide, I wrote the key as empty. So that has length 5. Okay, 5 letters are there in the key. So the period is 5. Let's say the period, if it would have been 4, then what would happen? So C will be mapped with key K1, R uses K2, Y uses K3, P uses K4, and then T again uses K1. Like that it goes on. So there is a period of 4 for which the key values are repeating. Now, it has to be the case to so clearly, if C is mapping to P using K1, then here also key K1, K2 are used only. So this is clear that it has to be the case that at position 198, the whatever the key value is, they start repeating from this position. So whatever is the length of the key, if it would have been 4, then it has to be the case that in between 24 and 198, a whole round is some whole number of round is completed. So the gap 198 minus 24, that has to be divisible by 4 if the key length would have been 4. Okay. So whatever is the length of the key in Vigenère cipher, it has to divide, right? I hope this is clearly visible from the example I worked out. So it is clear, right? Here is the occurrence, and the repeated occurrence starts from here. So in between this gap, whatever is the key length, so if key length is L, then this gap has to be the multiple of L, right? Now, what is this value? This is 4174, right? So 4, I was just talking about some random examples. So whatever options you have been given in the question, 5, 6, 8, 9, you have to check whether 5 divides 174. No. Does 6 divide 174? Yes, right? 6 divides 174. So 6 is the correct key length. You can check with 8 and 9 also. So 8 does not divide 174, neither 9 divides 174. So 6 is the correct answer, because if the key length is 6, then only, so it will have been like this. And so there will be repetition of, 29 times there must have been some characters there that will be repeated. And in the 30th segment, again the same K1, K2, K3, K5, K6 will have been used. Okay, like this. So this is one round completed. There will be again K1 to K6 completed second time. Like this 29 times you do this, and then again this cycle starts. So that is how it works. So 6 is the right answer. Next question. So it asks, which of the following statements is or are correct? Okay, let me just mention once that this Zoom link will be ending in maybe 7-8 minutes. So you can join in the same link, but after 10 minutes of gap. So Zoom does not allow continuous joining in the same link. So you have to wait for 10 minutes. You can consider it as a break and then join back in the same Zoom link. Okay. Whenever the meeting ends, after that, you wait for 10 minutes and then join back in the same link. Okay. Okay, proceeding to the next question, which of the following statements is or are correct? Any encryption scheme with key length less than message length cannot be a perfect secure scheme. So, anyone would like to answer just for the discussion purpose? Already the answers are posted on website, but still. Key length lesser than message length. Does that lead to perfect secrecy? Anyone can answer in chat. Yes, no. Is it a correct statement? That key length less than message length cannot be a perfectly secure scheme. Is this correct? Okay. So, yes, this is the correct statement because as you know that in OTP also we have seen that message length is or key length is exactly same as message length. In Varnam cipher also we have seen that key length is exactly same as the message length. So key length lesser than message length does not allow the scheme to be perfectly secure. So first statement is correct. Then a scheme is COA secure. So this is correct, right? A scheme is COA secure. Okay, there is some answer in the chat. Okay, yes, yes, you are correct. So, um, thank you for the answer. The next option you want to answer, a scheme is COA secure if and only if it is KPA secure. Is this a correct statement? Right. So, COA security does not imply KPA security, right? Okay. Why? Why is that? Because as we already discussed the hierarchy, so we start from EAV security, right? Cipher or ciphertext only attack, where you just see the ciphertext, nothing else. Then comes the KPA, where adversary has more power in terms of the fact that it has access to some plaintext ciphertext table. Okay, but it cannot control the entries of plaintext in the table. It just gets to know somehow pair of plaintext ciphertext. Okay, then comes CPA security, where again it can gather on its own such a table of plaintext and ciphertext with the extra advantage that which plaintext for that it wants to see the corresponding ciphertext that can be controlled by the adversary. So we say that the adversary has access to an encryption oracle so that it can choose a plaintext and can see the corresponding ciphertext. And then it is given a challenge ciphertext from which it has to infer information about the underlying plaintext. And then comes CCA security, where apart from encryption oracle, the adversary has access to decryption oracle as well. So here, not only there are pairs of plaintext ciphertext where plaintext can be chosen by the adversary, there is also a table of ciphertext, plaintext such that ciphertext can be chosen by the adversary and the corresponding decrypted value of the plaintext is visible to the adversary, with one constant is that the decryption oracle cannot be queried with the exact challenge ciphertext. Okay. After it has seen the challenge ciphertext, it cannot query the decryption oracle with the same ciphertext. That is the only constant in CCA security. So anyway, here the question is about COA and KPA security. Clearly, in KPA security, the adversary has higher advantage. So if a scheme is KPA secure, that is, even with extra power, the adversary is not able to infer information about the underlying message after seeing the ciphertext, then clearly with lesser power to it, where it does not have any access to plaintext ciphertext table, it clearly will not be able to distinguish the underlying messages by seeing a challenge ciphertext. So, if a scheme is KPA secure, then it surely implies the scheme is also ciphertext only attack secure. But the other way around is not true. So, ciphertext only security does not imply KPA security. So, because the statement includes this if and only if part, right? Which will be true if the both side implication is true, but this is not the case. So this is not a correct statement. And then for the third statement, given the one-time pad scheme, the scheme is still perfectly secure if on any subsequent invocation of the key generation algorithm, an earlier key gets regenerated. So this is a tricky question. Can anyone of you explain that how? So let me tell that yes, the scheme will still remain perfectly secure even if the key same key is regenerated in the one-time pad scheme. But also I mentioned that in one-time pad the key is never reused. That also I said. So what is the difference between that statement and the statement here that says even if the same key is regenerated in the one-time pad scheme, the scheme still remains perfectly secure. So this statement is actually true. It still remains perfectly secure indeed. But how? Why this regeneration of the same key does not affect the perfect secrecy? Anyone would like to comment on that? Maybe you can write in chat also. Okay, so basically what happens is that although, so how does OTP scheme gets defined? For any message M, you sample a new key, right? From the key space and your ciphertext is M XORed with K. This is how OTP encryption works. Now, after, so you now here you are let's say you are starting with message M1, okay, when you are doing this encryption first time with message 1, you are choosing some K1 uniformly randomly from this key space K and you are doing M1 XOR with K1 to get ciphertext. You again get M2 and you are choosing again uniformly randomly from the key space and you are doing this, right? So there may be a case for some MI, you get the key K1 again. But this is nothing but again sampling uniformly randomly. It's not that you are defining that this K1 I am going to use again. The key that I used for message M1, I am going to use that same key again for encrypting MI. That you are not specifying as your encryption algorithm, right? It again does the uniform random sampling over the key space. And there can be a case that the value selected here or chosen here from the key space is K1. But it is not sure whether this will be K1 or this will be K2 or some other thing. So this is not repetition that is specified by the algorithm. This is just occurs with the way we have defined the uniform sampling over the key space. So the strategy that we are using the key k, we are choosing the key k uniformly randomly from the key space and independently of the other keys chosen for some other messages. So that is what we mean by not reusing the key. Reuse is not specified in the encryption algorithm. Rather, it just happened to be the case that some ki is again selected while choosing from the distribution of key space. Okay. So that is why the scheme is perfectly secured. Nothing changes. Okay. Hope I am clear. And the fourth statement says that scheme is CPA secure if and only if it is CCA secure. So again, there is this if and only if present. I already discussed that CCA security will imply CPA security, because in CCA security, the adversary is more powerful. So even if with more power, if the adversary is not able to distinguish the underlying plain text after seeing the challenge ciphertext, then with lesser peer, it will certainly not be able to do that. So this implication is correct, but the reverse direction implication that CPA security implies CCA security, that is not correct. So this is not correct. That is why the if and only if statement is wrong. So the correct statements are 1 and 3. Okay. So this is your correct option. Mm. The last question for week 1 assignment: consider an instance of shift cipher with the probability distribution over the message space like this. So probability the message being so as you can see that probability of message being A is 0.25, probability of message being B is 0.5, and probability of message being C is 0.25. The total sum of this probability is nothing but 1. So clearly that implies that your complete message space is consisting of only 3 plain text value. Those are A, B, and C. So size of message space is 3 here. Now, this is a shift cipher. So what is shift cipher? If you remember that in shift cipher, we select a key value k from the space 0 to 25, right? From the set 0, I mean 0, 1, 2 till 25, representing the index for the English alphabet A to Z, 25, right? You choose a key randomly and that key is fixed. Now, each time you get some English letter as the plain text, let's say you get, so this is not the English letter key, rather this is a value between 0 to 25. Now, whenever you get some English alphabet, let's say you get C as the plain text. So what you do is that, uh, let's say the key was chosen to be 2. Okay. So the key of the shift cipher is 2. Then C is shifted by position 2 and gets mapped to E. That is how shift cipher works. Okay. So now this question was kind of discussed in the first live session also. So let me just recapitulate for this particular question that what is the probability that the ciphertext is D? Okay, the ciphertext is D. So how can that occur? There are 3 possible plain text, right? So let's say your plain text is A, then you will get the ciphertext as D, or you will get D as your ciphertext when your K will be 3, right? Then only A will get shifted by 3 position and mapped to D. And again, what will can be the another case, which is a disjoint case. So message can be B, and then what is the probability that ciphertext is D? That can occur only if the key is 2, right? Then B gets shifted by 2 position and then occurs. And the another case is your plain text is C and your K is 1. So C gets shifted by 1 position and maps to D. So these are 3 disjoint cases. And now probability of message being A is already given as 0.25. And what is the probability of key being 3? Because the key is getting uniformly randomly selected from this space 0 to 25. So the total 26 elements are there in the skip space, and there is uniform random distribution. So each key can be selected with probability exactly 1 by 26. And putting the values of again message being B, that is 0.5 into K being 2 is 1 by 26, like this. So finally we get 1 by 26. All these are summed up to 1. So the result is 1 by 26. So probability of the ciphertext D, probability that the ciphertext is D is 1 by 26. This is correct option. Probability that the ciphertext is A is 1/4 the probability that ciphertext is D. So this is wrong. Clearly you can see that probability that ciphertext is A will also have the exact same probability. That is 1 by 26. So it is not 1 by 4th of probability that ciphertext is D. So this is wrong. Probability that the ciphertext is D is half the probability that ciphertext is E. Again, due to the same reason, this is wrong. First option says probability that the ciphertext is D is the same as the probability that ciphertext is E. So this is correct. So clearly, first and fourth options are the correct ones. Okay. Proceeding to the next question. Uh, so we will enter the week 2 assignments now. So this is the first question in the week 2 assignment posted on NPTEL website. So the question says, let G be a secure PRG, then which of the following is or are a secure PRG? Where this symbol, parallel parallel vertical lines, so they denote the concatenation operation. I would like to ask the participants here if any one of them can comment on the security of first PRG proposed here. G1S is G of S1 XORed with G of S2. G is already known to be secure, and S is concatenation of two equal length strings. So S1 also has bit length n, S2 has also bit length n. So S is a 2n bit string. So seed of the PRG G1 has length 2n, and this is generating another string, that is G of S1 XORed with G of S2. Whether this will be a secure PRG or not. Any answer? Yes, no from the participants? Anyone? Okay, so basically what happens here is that G is already a secure PRG, right? So also it's provided that if you choose the seed S uniformly randomly from this space, so the first half of S, which is S1, and the second half of S, that is S2, they are also a uniformly randomly chosen seed, which is known only to the PRG, but it is secret to the adversary, right? The seed of PRG is the only secret. And the adversary gets to see the generated pseudorandom bit string. This is pseudorandom because for a secure PRG, seeing the PRG output, you should not be able to distinguish it from a truly random string, right? Now, because G is a pseudorandom, secure pseudorandom generator, so for a fixed seed S1, the string G of S1 is a pseudorandom string, right? And it is getting XORed with another pseudorandom string. So running the same PRG G with a different seed S2. And there is no correlation between S1 and S2. Okay. And so XORing two pseudo-random string again gives us a pseudo-random string, right? So the resulting generator G1 with the seed S, actually it generates a pseudo-random string. So yes, G1 is a secure PRG indeed. In the other way around, maybe you can show that if this was not a secure PRG, then you could be able to break the security of the PRGG. Okay, so you can find some reduction, so showing the security of G1. So it can be the case that let's say uh, you assume that the adversary is able to distinguish the result G1S from truly random string. Okay, so you have a distinguisher. So there is a challenger and there is adversary 1 and there is adversary 2. Here the PRG game for G is going on and here the PRG game for G1 is going on. Now this challenger is sampling uh, uh, this challenger is actually providing the value of G of S1. Okay. Okay. So okay. And then what this adversary can do, it can itself choose some other seed S2 and generate G of S2 on its own and then send it G of S1 or of G of S2. Remember, G is a public algorithm, so AD1 does not have any problem to run the PRGG with some S2 of its own choice and sends to this adversary AD2. And we already assume that AD2 is able to distinguish uh, this string from a truly random string. Now, what this string consists of? This is the XOR of mm, a. So let's say if the challenger would have chosen a PRG output, if it is actually a PRG output, so this is of the form G of S1, then this is pseudo random and this is also pseudo random. So you are actually sending XORing a pseudo random string with a pseudo random string, then it is equivalent to the output of G1 pseudo random string. And if challenger would have given it back a, so there can be 4 cases, right? So this challenger can choose to send to adversary 1 either a truly random string or a pseudo random string, that is output of G. And this adversary 1 also can choose 2 case, either the second string that it XOR with the output of challenger CH. So that string can be either truly randomly generated or can be generated by running G on S2 of its own choice. So among these 4 cases, you can just try to find out on your own whether there is a probability. So if AD2 is able to distinguish this output, which can be of the form truly random XOR with truly random or truly random XOR with pseudo random or pseudo random XOR with truly random. In any of this case, if AD2 is able to distinguish uh, this from this, then using that with non-negligible probability, AD1 will be able to tell whether initially a truly random string was selected or a pseudo-random string generated from PRG was selected. And then we can argue that with non-negligible advantage of this adversary 2, there is non-negligible advantage for breaking the PRG by the adversary AD1. But because G is already given to be a secure PRG, by contradiction, we can conclude that AD2 cannot exist, which is able to distinguish the output of G1 from truly random output with non-negligible probability. So such AD2 cannot exist, and thus we say that G1 is secure. Okay. So anyway, for the second option, so this is clearly visible, right? For the second option, the output of G2 is clearly can be divided into two parts, where first part is exactly equal to the second part. And using this probability, an attacker or an adversary can easily distinguish such a string from a from a truly random string of same length, right? So this can easily be attacked. So this is of course not secure. These also will not be secure. Why? Because clearly the output of G3 is nothing but a string of all zeros. Because GS is XORed with GS. So same string are getting XORed with itself. That is all string of all zeros. So clearly that is not a truly random output. So it is distinguishable from a truly random string. So G3 is also not secure. What about G4 is? So maybe I should discuss only. So G4S is concatenating G of S with the parity bit of S. Okay. X is the parity bit. It is a single bit. So whatever is the output length of GS, it is getting extended by 1 bit length, and that is the output of G4. Now, because the attacker has no information about the seed, this is secret. So the parity bit of S is also not known to the attacker. So because S is a pseudo-random, because S is a random string. Okay, if your seed is chosen from a L length bit space. Okay, so S is a random string of length L. Now, uh, the probability that parity bit of S, so what is parity bit? So number of ones present in the binary string divided by, modulo 2. So if there is even number of 1 present in this L bit length string S, then your parity is 0. And if there is odd number of ones present in this L bit length string S, then your parity bit is 1. So the probability of the parity bit of a random L bit length string S being 0 is exactly probability half, and being 1 also has exact probability of half. So the last bit of the PRG G4 can be 0 with equal probability as of the probability of being it 1. So clearly G4S is also another secure PRG. GS, this part is already known to be secure, right? And X is also a a random bit because it can be 0 with probability half, 1 with probability half. So together they construct a secure PRG G4. So basically G1 and G4 are secure. Next question, which of the following is or are not true about PRG? So first option says a PRG is a randomized algorithm. Second option says that a computationally unbounded adversary cannot determine the seed. Okay, so let's go by one after another. So first option is a PRG is a randomized algorithm. Quickly, please answer in the chat whether this is true or not. Quickly, I would expect you to respond. PRG is pseudo-random generator. So is it a deterministic algorithm or randomized algorithm? For the same seed S, the output of G of S, PRG running with the seed S, does it vary every time you run the PRG algorithm with the seed S? Is it deterministic or randomized? I would expect quick answer on chat, yes or no. I think this question was already discussed while we discussed PRG question in week 2 live session. Anyone? Deterministic, right, Obiru? Thank you for the answer. So, yes, PRG is a deterministic algorithm. We say it repeatedly that pseudo-random generator is a deterministic algorithm which takes a uniformly random seed as its input, which remains secret to the adversary, and then it generates a pseudo-random string. So with same seed, if you so why it is not randomized? Randomized means that if you run an algorithm with the same set of inputs, every time you can get some other output if it is a randomized algorithm. But if it is a deterministic algorithm, g of s always be the same string every time you run with the same input seed s. Okay, so it is deterministic, right? So this is wrong. Second option says a computationally unbounded adversary cannot determine the seed. Is it true or false? Answer from the participants in the chat. A computationally unbounded adversary cannot determine the seed. Computationally unbounded means the adversary can run for any exponential time. Runtime is allowed. Is unbounded. Okay, there is answer in the chat. False. Yes, correct. So unbounded adversary can always determine the seed. How? Because okay, there is another answer. False. They can determine. Hypothetically. What do you mean by hypothetically? Yes. So hypothetically means if it is allowed to have unbounded computational power, which is not practical assumption, but yes, if it is allowed, then it would be able to. Why? Because by exhaustively searching the seed space. So you are able to see the output g of s as an attacker. Now you know what is the length of your seed. So that is specified in your definition of PRG. So it maps maybe some m length bit string to ln bit length string. So you are seeing a ln bit string. Now you search for all possible binary strings of bit length m and try to see whether running g with, let's say, starting with all 0 to this all possible uh, values of m bit length string, you try running the algorithm g with that seed and try to see if that matches the output string you see. And exhaustively search the key space, you will certainly find the match somewhere. So it will take 2 to the power n time, which is exponential. Exponential with respect to the bit length of the seed, which is m. So computationally unbounded adversary can always determine the seed. A PRG is used to encrypt long messages. Yes or no? Answer. By long messages, we mean that your key length will be lesser than your message length, but you are still able to encrypt. Of course, in the computational world. In the perfect world, we need always the key space to be or key length to be exactly same as the message length. But in the computational world, okay, there is answer in the chat. True. Yes, you are right. So this is a true statement because how very basic symmetric key encryption algorithm. If we write, if we have key of say bit length L and we want to so let's say N, and we want to encrypt a message which has length some polynomial of m. Of course, L of m is greater than m, that is key length is lesser than your message length. Then what you can do, you can take some PRGG which maps your n bit length input to a L of n length bit output, and then so this is n actually, you can understand this is n. And what you can do, you can apply the PRG on your key K and then apply the XOR operation with the plain text M. So G of K is also having the bit length L of N and M is also having the bit length of L of N, and you can simply XOR them to get the ciphertext C. Now this looks like a OTP except the fact the key K is not completely or truly random of length ln, rather it is a pseudo-random bit string generated from a truly random n bit length string. So n is a small length than L of n, but still using the PRG, instead of generating a whole L length number of random bits, we just generate a smaller number of random bits and then use a PRG to extend it to a pseudo-random string of L of n length bits and then XOR the message of length this to get the ciphertext, right? So yes, this is a standard, or I should say, naive encryption algorithm uh, using PRG. Okay, and this is true. And then we can construct a PRG which is secure against a computationally bounded adversary. So we already discussed it is just the opposite statement to this. So if it is computationally unbounded, then it cannot determine the seed. But usually in computational world or in real world, the adversary has bounded resource, bounded computational power. So it is enough to make a PRG which is secure against a computationally bounded adversary, such that except with negligible probability, the adversary is not able to determine the seed of the PRG or distinguish the output of PRG from a truly random string. So this is also true. Okay. So for the next question, what do we mean by the term efficient adversary? So we were just discussing this. So quickly, I would expect the answer in the chat. What do we mean by efficient adversary? So we are repeatedly discussing that PPT adversary, probabilistic polynomial. The answer comes as fourth option. You are saying fourth option says running time of adversary is necessarily upper bounded by some polynomial and security parameter. If this is true, that's when we say it is efficient. So efficient means in reasonable amount of time, the adversary should attack the system. Okay. So running time of the adversary is necessarily upper bounded by some polynomial. If it would have been unbounded, then exponential running time would have been allowed, but that's not the case. For efficient adversary, its running time should be upper bounded by some polynomial. What others option says, adversary is very capable with almost infinite resources. Of course not. That is why we come to computational world and say that in real world, adversary does not have infinite resources. It has limited resources, so it is wrong. So this is also wrong, already said. Adversary performs its jobs effectively and efficiently. So this is not any way a formal statement. The formal statement is the correct statement is only the fourth one. So next question. Which of the following is or are correct? Now, this is first option 3 to the power minus root n is a negligible function. So is it a negligible function? Yes or no? I would then explain why is it so, but anyone could answer? It is a negligible function or not? Yes, it is negligible. Thank you for the answer. So, okay, again, I just repeat that if this meeting ends within 10 minutes, then please again wait for 10 minutes and rejoin back in the same Zoom link. Okay. So anyway, so yes, this is a negligible function. Why? That I will just explain in the next slide. See, so what is the definition of negligible function? So we say that if function delta n is negligible, if this is a negligible function, then for every positive polynomial fn, there exists an n0, which is a natural number n, so that for all n greater than n0, the value of delta n is less than inverse of this positive polynomial. That is how we define a negligible function. Now, if we want to prove that the given function, that is 3 to the power minus root n, is negligible, then I have to show that if I take any positive polynomial fn, so positive polynomial fn, let me just represent this polynomial fn in this format, n to the power k, where k is some constant. So this is a k degree polynomial, right? With the maximum power of n k. So or you can say, so any k degree polynomial, you can represent it as this. So let's say this is a function. This is a random positive polynomial function for some value k. Now I have to show that for this positive polynomial, I can found an n0, which is a natural number, such that value of this delta n is less than 1 by fn, that is inverse of this positive polynomial value. And of course, the negligible function takes as input a natural number n and outputs a positive real number, right? So this is a positive function here and output some real number. So what we do here is that I have to find such n0, or I have to prove that there is always an n0 for any positive polynomial you take. So I take a random positive polynomial which is n to the power k. So what is inverse of this polynomial? 1 by n to the power k. So my given function is 3 to the power minus root n. So that is 1 by 3 to the power root n. That should be lesser than 1 by n to the power k. Which you can write as taking log both sides, you get minus root over n log 3 lesser than minus k log n. You just remove the minus symbol and you get k is lesser than root n log 3 by log n. Now, for any value of k is some constant value. You can take k to be 2, you can take k to be 1000 also. So, but whatever value of k you take, you will always get a natural number a natural number value of n such that this expression surpasses the value of k or is greater than the value of k. So in this graph, I just plotted this y equal to root n log 3 by log n. This is a plot for this. And let's say I take k equal to 2 just to see what will be the value of n0 if my positive polynomial fn is of order of n square, okay, k equal to 2. So just to show that there is always a such value possible such that root n log 3 by log n is greater than 2. So in the graph, you can see that, so this is the value 2 in the y-axis. I don't know if it is visible or not. This is value 1, this is 0, minus 1. This is the y-axis. And here it is 50, and you can see that maybe around 52, this this x-axis at y equal to the horizontal line for the y value of 2 is crossing this line, okay, right? So this is there somewhere around 52, it surpasses the value 2. So we can say that, let's say n0 is 52 here, because for all n greater than 52, your value of the function is always greater than 2. So y is always greater than 2. So if you take k equal to 3, somewhere far right from here, you will always get some value of x where you will see that the y value of this function is crossing the value y equal to 3. Okay. So like that, you will always find some n0 for any positive polynomial you take. So that is why 3 to the power minus root n is indeed a negligible function. For the other option, so let me say that the last statement, n to the power minus log n is a negligible function. Yes, this is also another negligible function, and you can just show in a similar manner. So n to the power minus log n, right? So you will show that 1 by n to the power log n, right, must be less than 1 by n to the power k for some positive polynomial if n equal to n to the power k. And then again, similarly, you get this, it's like this, and you take log both sides. So you get log n so you will always find some value of n such that value of log n is greater than the value of k, right? So this is very easy to find rather, okay? So anyway, this is how you show that n to the power minus log n is indeed a negligible function. Coming to other two options, second statement says that distinguishing ability of the adversary is defined as its ability to distinguish between an encryption of 1 versus an encryption of 0 with probability much greater than half over a message space of 0, 1. So is this a correct statement? Quick answer on the chat, I would expect. When we say that adversary is able to distinguish uh, encryption of 1 from encryption of 0, then what does it mean? So, any answer in the chat? So, okay, this is indeed correct, right? So, whenever we say that there is answer in the chat, yes. So, yes, your answer is correct. So, yes, whenever we say that the adversary is able to distinguish, that means that with probability much better than half, because when we say that adversary is not able to distinguish or the system is secure, that means that the distinguishing advantage of the adversary is negligibly greater than half. But if it is not secure or the adversary is able to distinguish, that means that with significant probability uh, greater than half, the adversary should be able to distinguish the system. So this is a very basic statement, which is true. The third state, so this is true, and the third statement says that while using a PRG, same key can be used for every instance of encryption. So is this a correct statement? In the chat? Sarah is saying yes. So yes, it will be secure, but then we need to see that whether we are talking about a single message NDAV security or multi-message NDAV security. All these things we need to consider. But yes, in general, same key can be used for every instance of encryption because we have the fixed key K and corresponding GK is also fixed. So for each MI, I can just XOR it with MI. But point is that GK, because this is a deterministic thing and your GK will be fixed. So if you are looking at multiple message, mult in EAP security, that is NDAP security in presence of multiple message, then it can be problematic because this scheme is deterministic. But otherwise, yes, same key can be used for encryption. Okay, so in general, we can't say that this is a correct statement. The reason being this. Okay. So this is, so as I was saying that for generically we are using PRG, you cannot use the same key for every instance of encryption because that will not lead to your DAP security, okay? Because the scheme is deterministic. So only correct statements here are 1, 2, and 4. Okay. So proceeding to the next question. It says difference between perfect security and semantic security involves one or more of the following. First option is bounds on how long the adversary can run the experiment. So is it true? So does the bound on how long the adversary can run the experiment is different in case of perfect secrecy and semantic security? Quick answer in the chat. So semantic security is corresponding to the computational secrecy world. So, okay. So this actually differs in both the cases, right? So as we were always saying that in perfect secrecy, we assume the adversary to be unbounded. So it will have unbounded computational power, it will have infinite resources, but in semantic security case, in the computational world, we always deal with bounded adversary whose running time is upper bounded by some polynomial function, and also it has finite resources. So yes, how long the adversary can run the experiment, that differs between these two cases. The next okay, then the third option also says bounds on computational capabilities of the adversary, which is again true. The second option says in the respective indistinguishability experiment, adversary has the exact same probability of success. Is this correct or not? Anyone would like to answer in the chat that in the indistinguishability experiment, so in case of perfect, so what is the indistinguishability experiment? If you remember, there is a challenger and there is an adversary. For the encryption scheme, the adversary actually provides the challenger with two messages of its choice, and challenger then tosses a coin to determine whether to encrypt M0 or to encrypt M1, and accordingly it encrypts that corresponding message and outputs or sends to the adversary the ciphertext CB corresponding to a message MB, where MB can be either M0 or M1. Now the adversary's task is to guess a bit B dash, and adversary wins the game if it is able to correctly guess the bit B dash. That is, if B dash is equal to B. So adversary has to guess whether it is seeing an encryption of M0 or it is an encryption of M1. Now, in case of, this is the indistinguishability experiment in both the cases actually. Now, the adversary's probability of success, how does it differ in these two cases? Anyone would like to answer in the chat? In perfect secrecy world and in computational secrecy world. Is it same or is it different? The adversary's probability of success. That is, adversary is able to guess bit B dash correct. Okay. So if it is a perfectly secure scheme, then the adversary's probability of winning is exactly half. Okay. So adversary can always randomly guess a bit B dash between 0 and 1 and replies with that. So that has the probability of winning half, but nothing more than that. It is exactly half in case of perfect security. But in case of computational security, we say that the adversary's winning probability can be negligibly greater than half. Okay. So they are different. We compromise a bit in computational secrecy world. We can allow the adversary to have negligible amount of uh, advantage in this game. So more than half, it has some more probability which is negligible function. Okay, so they are different actually. So this statement is wrong. It's not seen. Okay. Now assignment questions from week 3 I will discuss. So starting with the first question. Which of the following is or are true for one-way function, OWF? So you can answer in the chat. Are they are deterministic function? Is this true or false? Quickly. OWF, one-way functions, are they deterministic or randomized? Okay. Uh, True. Yes, you are correct. This is true because whenever we talk about function, the function should always be deterministic. Okay. With the same input, it should always output the same value as the output. So yes, OWF is deterministic. OWF can be many to one function. Is this true or false? Many to one, right? So two different elements from the domain can map to the same element in the codomain. That is many to one function. So can a OWF be many to one function? There can be two cases, right? Either many to one or one to one. This like this. This is 1-to-1 case. So can OWF be many to one? Yes, it can be. Okay, it can be many to one. Only so what is OWF? In OWF, you again we have this challenger and adversary concept. So the challenger uh, can choose a random x and compute its corresponding fx, and then this valued element of codomain is given to the adversary. Now adversary has to guess x dash from the domain of the function f, and if is a one-way function, if the probability that f of x dash is equal to f of x that the adversary had seen is negligible. Okay, so upper bounded by negligible. So that is that for the adversary, guessing a correct pre-image of the value fx is should be hard, or this can be done with this cannot be done except with negligible probability. So it can be many to one. In that case, we say that there can be multiple pre-image of a same value y, but any one of them, if adversary is able to guess with non-negligible probability, then it is not secure. But it can one-way function can be many to one function. This is true. A one-way permutation is an one-way function which is also a bijection. So of course, this is also true because one-way permutation can be thought of a subset of one-way function. Okay, so one-way permutation is also a one-way function. Only difference being that in OWP one-way permutation, it's a bijection. So it's 1-to-1 and on-to. So all the elements of the range has a valid pre-image in the domain of the function. So this is on-to. There is no element who does not have any pre-image, right? So 1-to-1 and on-to mapping, it is permutation, right? So basically all the elements in the domain will have some element in the codomain, right? So this is true. And the fourth statement says the time complexity to compute the inverse of OWFs is a polynomial function of the security parameter. So this is a very clear true or false statement. Anyone to answer in the chat? Is this true or false? That computing the inverse of OWF is a polynomial function of security parameter? True or false? So what is meant by polynomial function of security parameter? That would imply that it is easy to compute inverse of OWFs. If I am saying that inverse of OWF is a polynomial function of security parameter, I mean to say that computing inverse of OWF is an easy task. But we know that that is how OWF is defined, right? So computing fx from x is easy. That's one way. X to fx is a easy thing. But seeing fx, computing some pre-image of fx, this is hard, right? So that is a contradictory statement. It cannot be a polynomial function of security parameter. It is always exponential function, right? So this is wrong. Okay. First three statements are correct. Which of the following candidates is or are essentially secure PRFs? In all the following options, if S X is a secure PRF, where X and S are in bit length string and output is also in bit length string. So you are given a secure PRF F, where S is the key and X is your input. And now you are trying to define another PRF G, which also uses S as its key and X as its input. And the PRF is defined in this way, whether the PRF G is a secure or not. So anyone would like to answer? this is kind of recapitulation of the week 2 live session. Okay, so I would appreciate if anyone would like to answer in the chat. Basically, if you are saying that G is not secure, so let me say that G is not secure. Now tell me that how do you attack this PRF, or how do you distinguish output of G from its output of truly random function? So in PRF, what is the security game going on between a challenger and adversary? In PRF, the adversary is allowed to query the challenger with inputs of its choice, and in response, it is able to see the corresponding PRF output. And after polynomial number of repetition of such query phrase, the adversary, so basically this can be either PRF output or some random, truly random output that let's denote it with yi. So the adversary challenger decides in the very beginning of the game whether it is going to send to adversary PRF output or TRF output. It is decided in the beginning of the game. And accordingly, for each query xi, it sends to adversary either PRF output or truly random output. And at the end of the game, the adversary's task is to decide whether what did he with which did he communicate, whether it communicated with a PRF oracle or a truly random function oracle. Okay, so it guesses a bit B. Now, if adversary is able to guess that is able to guess correctly with which it was interacting, a truly random function or pseudo random function with non-negligible probability, then the adversary wins, and we say that the PRF is not secure. Now, for this particular example, how the PRF G's security can be broken. So, the adversary here can query the challenger with some xi, and if the challenger has decided to respond to the adversary with PRF output, then the output will have the format of fs of xi XORed with fs of xi bar. Xi bar is complement of this binary representation of xi. Okay. Now, if it is truly, it is actually interacting with a PRF oracle, then it repeats the query. So adversary does not know whether it is interacting with a PRF oracle or a truly random function oracle. So it again queries the oracle or queries the challenger with xi bar, and in response, it gets some yi. So in response, in the first case also, yi can be of this form or it can be any random thing. And in the second case also, if it is the challenger uses PRF to generate the output, then it will have this form xi double bar, that is xi itself, or it will be some ri dash, another truly random output. Okay, so now see that if it is interacting with a PRF, then always with probability 1, these two value will be exactly same. And if it is a truly random function output, then these two value will be same with some negligible probability. That is, let's say the output has bit length of n, then your two n bit length string are exactly equal. That has probability 1/2 to the power n. So in case the challenger was using PRF to generate the query responses, then this distinguishing strategy of the adversary to follow whether the output it sees for xi and xi bar are same or not, and according to that replying that it is interacting with a PRF or TRF, that strategy will work with probability 1. So we can say that probability that adversary wins when PRF was chosen, that probability is exactly 1. And probability that adversary wins when truly random function was chosen, okay, that probability is 1/2 to the power n. So distinguishing advantage of the adversary is 1 minus 1 by 2 to the power n. So difference between these two cases, which is clearly not negligible, right? So that's why we can say that the function g defined in this manner, fs of x XOR with fs of x bar, that is not secure here, because the system can be broken with this strategy by the adversary. Now coming to the second question. Basically here, let me tell you that G will be secure here. Why? Because just imagine that if G would not have been secured, then using the distinguisher for G, you could have find another uh, distinguisher which is able to distinguish the uh, output of PRF from truly random output. Okay, because the FSX is itself being used as a key to the PRFG. Okay, so that is why security, uh, the insecurity or the fact that GSX is not secure, that is, there exists some distinguisher who is able to distinguish output of GSX from truly random function output, will imply existence of another adversary who is able to uh, distinguish FSX from truly random output. So GS of X is not secure will imply FS is not secure. But then we already know F to be a secure PRF, so we conclude that G is a secure PRF. Okay. For the third one, so anyone would like to answer whether this is secure or not? So see that F is already known to be secure. So F of X for the key S1. Of course, S1 and S2 are not related to each other. They are independent string. Now you run PRF on input X with a key S1 and then XOR the output with the output of running F on the same input X but with a different key S2, independent key S2, and you XOR these two pseudorandom values. So since F is a PRF, the output is a pseudorandom value, and since and for the same reason, this output is also another pseudorandom value, and you are XORing these two pseudorandom values to generate another pseudorandom value, as we had also seen earlier for an example of PRG also. So here also similar things are happening. So that's why G remains secure. Okay. Uh, so this is secure, this is secure. And for the last one, you are always concatenating the output of a secure PRF F with a 1 at the beginning. So you concatenate 1 with the output of F of S of X. So although this is a pseudorandom thing, but your first bit of the output of G is always 1. So in fact, so if I compute the distinguishing advantage, so in case uh, G, so the challenger in the game of G, if it decide to send uh, PRF output to adversary, then the adversary can check whether the first bit is 1 or not, and responds with yes, I am interacting with a PRG, and that strategy works with probability 1. But in case that challenger chooses to output a truly random functional output in response to the query of the adversary, and then adversary finds the first bit of the string to be 1, that will occur with probability half, because for a truly random string, first bit being 0 or 1, that occurs with exact probability half. So it will be 1 with probability half. Now the difference between the two, which denotes the distinguishing advantage of the adversary for the security game of the proposed PRFG, that distinguishing advantage is 1 minus half, that is half, and which is clearly not negligible. So that's why your G of S of X, this proposed PRF is not secure. Okay. So proceeding to the next question. Select the incorrect options. Trivium is a hardware-oriented stream cipher. In the CPA security model, the adversary is allowed to interact with the encryption oracle a polynomial number of times. RC4 cipher is a practical instantiation of secure PRG, and encryption algorithm in any stream cipher is randomized. Which of them are correct? You answer. You can answer in the chat. Among these four, which are the correct ones? Which are the correct ones? Anyone? No? Okay. So, basically, first and second statements are correct. So, trivia is a hardware-oriented stream cipher. I have nothing to explain in this. This is just a fact, and a little bit discussion about trivia is there in the lecture also. So, this is indeed hardware-oriented stream cipher. This is true. And in the CPA security model, the adversary is allowed to interact with the encryption oracle a polynomial number of times. This is also true. Why? Because we already said that we are in the computational world for CPA security model, and we allow the adversary access to the encryption oracle, but for how many times? Only a polynomial number of times, because the adversary is PPT adversary, we write, right? Probabilistic polynomial time adversary. So if it is allowed to query more than that, then it will become it will not remain anymore a polynomial time adversary. So in polynomial time, it can make polynomial number of queries to the encryption oracle. Okay, so this is this is correct. This is correct. RC4 cipher is practical instantiation of a secure PRG. Uh, this is not correct because RC4 has proven to be not secure. And the last option, encryption algorithm in any stream cipher is randomized. We already discussed that for a fixed key K, the PRG output or the stream cipher, the pseudo-random stream G of K is fixed because G is a deterministic algorithm. And then the way you define this stream cipher, it is deterministic, right, for the fixed value of key K. So it's not randomized algorithm. So, okay. Only first two options are correct. Now, next question, let pi consisting of three algorithms, gen, encryption, decryption. Keygen, encryption, decryption is a symmetric key cipher. And then consider a variant pi dash with the same keygen, encryption dash and decryption dash of pi. So keygen algorithm remains same, and encryption dash m is defined as encryption k on reverse of m. The steps of decryption dash are performed accordingly. Here reverse of m denotes the bit string obtained by reversing the order of bits of m. So if let's say m is 110, your reverse of m is 011. As simple as that. Okay. Now, if now the options are some statements are given that if pi is multi-message COA secure, then pi dash is also multi-message secure. Whether this is true or not. So basically, we show that yes, pi dash will also be multi-message COA secure, because if it is not, that would imply, so if pi dash is not multi-AV secure, so ciphertext only attacks security and eavesdropper security is the same thing basically. So if PIDAS is not multi-AV secure or multiple message COA secure, then that implies that there is a distinguisher D who, after seeing a ciphertext CB, is able to distinguish whether it is seeing an encryption of M0 or M1 with uh, with non-negligible probability, right? Or in other words, after seeing a ciphertext C, we can say it can retrieve meaningful extra information about the message distribution, right? Probability of M being some M for the corresponding ciphertext C. So it can gain extra information about the underlying plain text of C. Then we can use this distinguisher to design another distinguisher for the scheme pi. Okay, how is it possible? Because if we can gain information about the distribution of reverse string of M, then clearly we can gain information about the actual string M. Okay, because message space is the same. If you know the distribution of reverse of M, you also will know the distribution of M. So using the distinguisher for pi dash, uh, we can create another distinguisher for the scheme pi. Then pi will not be any more multi-message CUA secure, but it is already provided that pi is multi-message CUA secure. So by contradiction, we say that pi dash is also multi-message CUA secure. Now, the next option is for single message CUA security. And again, this argument goes in the same way, but the statement is opposite here. It is saying that pi dash may not be single message CUA secure, which is not true. So this is your, this is correct. This is not correct. If pi is CPA secure, then pi dash is also CPA secure. So in CPA security game, what happens is that the adversary has access to encryption oracle, right? So if I have adversary who is able to break the CPA security of the scheme pi dash, I will be able to design another adversary for the for breaking the CPA security of pi. And how is that possible? So basically, let's say there is a challenger, there is adversary 1, and there is adversary 2. And here the game is going on between for the game pi, and here it is going on for pi dash. And now adversary 2 sends mi, and adversary 1 provides reverse of mi to this challenger. And then in the result, encryption of this reverse of mi is returned to adversary 1, and it forwards the same result as CI to adversary 2. Now adversary 2, from the viewpoint of adversary 2, for each message mi, it sees the encryption of this form, encryption of reverse of mi, right? So that is exactly how the encryption dash scheme is defined. So for adversary 2, uh, it is creating an attack against the scheme pi dash, and if it is efficient, if it is able to distinguish successfully this thing, then it is able to tell in the challenge phase. So basically what happens in the challenge phase, this is the query phase, right? So for chosen message, the adversary is able to see the corresponding ciphertext. Now in the challenge phase, again, the adversary 2, sends two message M0, M1, and here adversary 1 sends reverse of M0 and reverse of M1, and whatever CB it receives, it forwards the same to adversary 2. And seeing the CB, the adversary is able to tell whether it saw the encryption of M0 or encryption of M1 according to the scheme encryption dash. And the same answer will be provided by adversary 1 to challenger, same bit. And if adversary 2 is successfully determined whether it saw the encryption of M0 or encryption of M1, then adversary 1 is also able to say whether it saw encryption of reverse of M0 or encryption of reverse of M1. So with exact equal probability, the adversary AD1 can win the game as of the winning probability of adversary 2. But we already know that adversary 1 cannot win this game with non-negligible probability because pi is given to be CPA secure. That's why we conclude by contradiction that pi dash is also CPA secure. And similar argument goes for CCA security as well, but the fourth statement says that if pi is CCA secure, then pi dash may not be CCA secure. So pi dash will be CCA secure actually. So this is also wrong. Only first and third options are correct. Coming to the last question for week 3 assignment. Which of the following statements is or are correct? If a PRG exists, then so does one-way functions and vice versa. So, well, this is true because so in the lecture we already had seen that how you can construct PRG from OWA, and given a PRG, how you can construct another one-way function, right? And then, so this is true. So the examples for how you can do that are already discussed there in the lecture. And determining the sign of x for x belonging to R given x squared is an example of hardcode predicate. So what is hardcode predicate? Basically, as we know of one-way function, so for one-way function, we say that given fx, determining a correct pre-image of fx, some x dash, that task for an adversary is hard, right? So it cannot do that except with negligible probability. Now, so here basically you need to guess a value of old x, right? But in case of hardcode predicate, given fx, so there can be case where uh, an attacker cannot determine the whole value of x in its exact form, but there can be some function of x which can be easily retrieved by seeing fx, partial information about x. However, hardcode predicate uh, defines those functionalities which are difficult to achieve given the value of f of x. So formally, if f is a one-way function, then its corresponding hardcode predicate hc is a function. It is a function which why is it predicate? Because the output of this function is always binary. H of x always belongs to either 0 or 1. So it can be thought of having some truth value, true or false. That why it is called predicate. Okay, its output is always binary. Now hcx is a hardcode predicate if with the knowledge of x, it is always easy to compute hc of x, but with the knowledge of fx, it is hard to compute hc of x. So hardcode predicate uh, represent those functionalities of x which are not which are hard to be found out by seeing the value of f of x. Okay. Now, for this particular example, if you know that x is a real number and you are seeing the value of x squared, you can of course perform the square root operation to find some x, but whether it has a sign of plus or minus, you cannot determine, right, with non-negligible probability because both x and minus x maps to the same value x squared. So indeed, it is a hardcode predicate. Next statement says a single message CPA secure encryption scheme is also multi-message CPA secure scheme. Yes, this is true. Why? Because you can think of the encryption oracle service for CPA secure encryption scheme as the multi-message, the availability of multi-message encryption facility as well, right? So if a CPA secure scheme is single message secured, it is bound to be multi-message CPA secure as well. Okay. And then secure PRGs can be constructed using secure PRFs and vice versa. So this was true, and this is also true. Why? Because you have already seen the construction for from PRF to PRG and from PRG to PRF. All these are nicely discussed in the lecture. Okay, and so very quickly I would like to discuss. So that's all for the all as NPTEL website assignments provided for all the 3 weeks. There is a bonus question, so just quickly we can take a look at it. So F is a secure PRF given which takes the input of bit length n, the input of bit length n and also key of bit length n. Now f dash is another PRF that you are trying to propose, where f dash has input space of length n minus 1, and then you use the function f to define f dash as this. So there are two proposed pseudo-random function here, whether of any of them are secure or not, secure PRF or not. So maybe I can just quickly discuss the answer. So first one is secure. Why? Because X is input and you are, because F is a PRF, right? So the output of the PRF is pseudo-random. That means its relationship with its corresponding input is not clear, right? So it cannot be determined in efficiently. So if you are using the input x of bit length n and then just running f twice, so that does not actually affect the pseudo randomness of the output. Okay, so you can show it by contradiction, but the interesting thing is that here in the second case you can actually attack the system. How? By choosing properly the input. So if you choose x first to be 0 to the power n minus 1, then what is the output of f dash? It will be fk of 0 to the power n concatenated with fk 0 to the power n minus 1 and 1, right? So first n minus 1 bits are 0 and then 1 at the last. And then you do another query to the PRF function oracle with this string, that is 0 to the power n minus 2 and 1. Then what is the output of PRF? If it is a PRF that is interacting with the adversary, then it becomes 0 to the power n minus 1, 1 concatenated with fk of 0 n minus 2, 1, 2, n minus 2 number of zeros and 2 ones. So now looking at these two outputs, the first half of the second string and the second half of the first string will be exactly same if it is interacting with a PRF with probability 1. But if it is interacting with a TRF, the adversary is interacting with a truly random function, then this is a 2n bit length string and this is a 2n bit length string, and the probability that the second half of first string is exactly equal to the first half of second string will be total 4n bit length string, and this will be